Hello, everyone. These after-lunch sessions are always a bit tricky because there is always a good chance that no one will show up. So thank you all for coming. So yeah, I'm going to try something before I start with the topic today. Actually, Dobar dan, Novi Sad. Have I said that correctly? I'm just kidding. I'm from Serbia, actually. Uh, my name is Nikola Živković. I'm working at the team at Vega IT Sourcing. We are a golden partner. There is a big, nice bolt out there. Yeah, so I'm working as a team leader right now. Also, I've been working in the industry for 7, 8 years or something like that. Working on a smaller projects, bigger enterprise projects, and these days I'm kind of doing a little bit of data science and kind of making a bridge between standard development and data science more accessible to everyone. Also, you can follow my blog, rubikscode.net. I try to write at least once a week, or you can follow me via Twitter using that handle over there. Also, I'm having several courses on packed publishing, so you can check that out as well. So that would be all from the marketing part. Now let's start with our big topic today, machine learning. It's all rage and party, isn't it? Everywhere we go, it's quite a buzzword. Every conference is having at least several topics on machine learning. And today we are going to cover several parts of it. Actually, I'm going to talk about why should we learn machine learning at all. How does it work underneath a little bit, and then I'm going to show what would be like the process when you get the real data and you should do something about it and do some kind of predictions or classification. Also, I'm going to try to debunk some of these like doomsday scenario that are been in the media lately. So why should we learn machine learning apart from extreme fear of missing out, which I have. So one of the biggest reasons is probably that machine learning as a field is kind of crossing the chasm today. We are going from early adopters to early majority. There are a lot of people using machine learning to actually make real practical solutions today, not just for sciencey stuff. So it is becoming more and more engineering technique and less research technique. So I think that's really important, and I think we are in a great moment right now to start actually learning it and to use it for real stuff. Also, I guess you all know this, there is a lot of data coming today. We are producing more data than ever before, and that is probably the reason why should we get into data science in the first place, and to demonstrate something. From the beginning of time until 2005, we as a human race collectively produced 130 exabytes of data. Now, exabyte is a real word. I checked it. It's not, like I said, gazillion of bytes. So it's actually 10 on 18 bytes of data. And to try to paint a picture here, if we cut down the whole Amazon forest, now I'm not saying we should do it apparently, but I'm just trying to prove a point very poorly. If we cut down every tree in the Amazon forest, make a paper out of it and print some data on it, we would actually get just 1 exabyte. So from the beginning of time until 2005, we produced 130 exabytes of data, which a lot of changed in the following years. So up until 2010, we actually have 1,200 exabytes, and up until 2015, we had 7,900 exabytes of data. And predictions are coming. Also that up until 2025, we will have 193 zettabytes of data. So yeah, also a real world. And we are having a lot of data. We are having a chance to take a look at that data from a different perspective. And because we as humans cannot, sometimes, make sense of all that, machine learning actually can, and that is really important. So We are not just having the technology, we are having also a lot of data which we didn't have before. And machine learning is not a new science. It actually comes back from early age. For example, Bayes' theorem that we are using heavily today is from the 18th century. Markov chains were 1913. And the whole idea of learning machines are coming actually from the 50s and from the Turing machine and from the perceptron. So it's not like we are having a lot of knowledge there. It comes from more than half a century of knowledge. So why haven't that boomed? Like machine learning that didn't boom in 50s was because the hard disk of 5 megabytes looks like this back then. And basically they didn't have a resource to actually make all these things happen. So we are at the pivoting point of history. So it seems we are having a lot of data, we are having the resources, and we are having a lot of knowledge. So we can actually make real-world problems solvable using machine learning, and avoid those doomsday scenario with Terminators and Matrix and stuff like that. So it is up to us, right? And I think we are at the great point of time to actually do these things. So what is machine learning? Of course, it is a branch of computer science which uses statistical techniques to give a computer ability to learn without explicitly program it. So how does that? We do that. Basically, we give our machine learning process a lot of data, and we create something that is called machine learning model, which is also actually just a mathematical model which can approximate that data. And we are doing that in a few types of learning, so to say. We are having several learning processes. The first one is supervised learning, where we give our machine learning model input data, and we also give the output data. And we say, OK, these are the expected results. And after a while, our machine learning model will actually know how to predict, how to classify data, or how to give us some sort of recommendation or something like that. The other type of learning is unsupervised learning, where we just put a bunch of data to the machine learning model and say, OK, here it is, just figure this out. I don't know what it is. So then it is able to either classify data or do some kind of predictions or something like that. And finally, we are having reinforced learning. That is something that actually Google used in his, what is it called? AlphaGo, yeah. AlphaGo, which is a neural network which beat the world champion in the world of Go, a couple of years ago. And the Go is like some kind of complicated chess. Never really got into that, so I cannot tell. But anyway, today we are going to see one example of supervised learning in our real-world data that we will get. We will use this type of learning to try to make predictions of our new predictions of our data. So as I mentioned, machine learning is actually solving two types of problems. The first one is classification or clustering, sometimes it's called like that, or regression. And this is exactly the situation. For example, if we have like two features of our data, two stuff that our data is describing, we are trying to create this model, which is actually just a mathematical function. Now, this is really simple example where we have just a linear function. And it splits our data into like the red ones and the blue ones. And then if we push a new information with gene 1 and gene 2, I don't know what this actually represents, values, we will be able to classify it and say, OK, this is a blue dot or a red dot. Or the other type that we can do is regression, which is something that's usually time-based. For example, if we have like stock market predictions, or we want to predict what the values of some, I don't know, company will have in the future, we can do that by doing a regression problem. So using some kind of features to like plot more numerical value in here. We are also creating some sort of, sorry. we're also creating some sort of a function here, and again, this is a really simple example. What we usually have is actually we are having more features than these two. We are having like, I don't know, multiple information about some topic, and we are actually having some multidimensional spaces in which we are creating not just a straight line, but I don't know, some kind of multidimensional plane, which will actually split our data, for example, in two parts, which is not something that we can present or understand very, very, very good, but machine learning models can. And today we are going to observe one set of data that we will try to solve. We will try to create some kind of predictions. We'll see later how that looks like. But what I wanted to put an emphasis on this is that we will actually follow 3 steps. The first one is the most important actually part, because we will analyze the data and we will see what do we have in our data set, what is the essence of a data that we have. And using that, we will be able to, modify it and tweak it to actually be useful and for our machine learning models who can create good predictions. And then we are going to use proper algorithms. Now, I won't go into algorithms in this presentation because there is a lot of information online about them. And we are also having great tools which are predefined. And in this case, we will use Sci-Kit Learn from Python library, which already has classes which do all this magical stuff for us, and we don't have to worry too much about it. And then we will see evaluation of that model. So we will see how it performs and should it be better or should we do something about it. So data analysis itself is having a few steps. First, we are taking a look at each feature of data that we have, and we are analyzing what it is, what it represents. Is it sort of enumeration, or is it numerical data? Then we are checking if there is a missing data in our data set, and we are doing some kind of treatment of it. For example, we are replacing missing values with mean value of that feature, or we are replacing with maximum or minimal value. Then we are detecting outliers. Outliers are samples which have values which vastly differs from the majority of it. And we are trying to see if should we remove it from our data set or should we keep them. And finally, we are doing the correlation analysis, which is we are looking at those features, how they are applied to each other. Is there any connection between them, and can we remove one feature and make work for our machine learning model a little bit easier, because I said multiple dimensions, and calculation in multiple dimensions are not easy, and they are requiring a lot of resource. And then we will apply algorithms. I said we will use 3 of them and see which one of them performs best. So we will use classical logistical regression, then we will use decision trees, and finally we will use random forest algorithm. Again, won't go into them because that will take too much time, but you can check them out online. And then we will evaluate how those models performed by using this root mean square logarithmic error function. It sounds really complicated, but it's actually not. And we will see how our prediction, what we predicted and what was the actual value for the thing we try to predict. And we will calculate this value. It is really, in this case, it turned out like the best evaluation process that we could have. So what will we check out today? We will check data from bike sharing demand systems. That is those systems are like a rental systems in which you can go to city and you rent a bike in one place and return it to another place. And they have like memberships and stuff like that, but they are also collecting data, which is really cool because using that data we can observe what kind of traffic will be in the city for that day or something like that. And also what we will do today is actually we will try to predict based on the weather data how many bike rentals we will have for each hour. And this bike sharing demand data is actually hosted on Kaggle and UCI. These are database repositories, and you can download it and then play with it and do all kind of fun stuff. And it is hosted by the Capital Bike Share. Yeah, I forgot to mention that. That's one of those bike rental systems from Washington. And here it is. This is how that data looks like. It's a little bit prettified here. But in essence, we are having like several features in it. We are having, for example, a season, which is enumeration that says which season we are. I think 1 is for winter, 2 is for spring, 3 is for summer, and 4 for autumn. We are having a year. 0 is for 2011, and 1 is for 2012. That is because for that 2 years we are actually having values. We are having a month, an hour. Was that a holiday? Was that a week? Which week day was it? Was it a working day? What was the weather? This is also some kind of enumeration. I will show you later what it represents. We are having a temperature, self-field temperature, humidity, wind speed, and we are having finally how many casual and how many registered bike rentals we had. And the final column here is actually our output, or how many bike were rented in that hour. So that is actually the value we are going to predict, and that is called dependent variable because its value is actually depending on all others in our data set. So we are having 15 independent variables, which we show later. They are not depending on each other, or at least that is what we think. And we are having one dependent one, which is output that we want to produce. And yeah, this bike sharing demand data set is actually consisting of two files. The first one is having our track, and the other one is having a day track of number of bike rentals. And we will use just the hour one because it will simplify this presentation. So yeah, finally, before I go any deeper, technologies that we are usually using and actually that I used in this presentation is actually Python 3.6. I used a Sci-Kit Learn library for all the machine learning classes and stuff like that. And also I used Jupyter Notebook for the presentation. So what I've done, I actually already run the code. So I will just switch for a little bit. You see this? Yeah. Okay, this is a Python Jupyter. It is actually an editor that is opened in Google Chrome. So this is a Chrome page. I just full size it so you can see. And it is really cool because you can also, you have different cells of code that you can run. For example, this is one cell of code which can be run, but also you can add these like text cells. So it kind of gives you this cool approach in which you can have a code and documentation in the same place. So what I've done first is I actually imported some necessary modules. For example, I imported calendar and date time, which of course are just for processing that kind of information. I imported NumPy, which is a Python library for numerical operations. I used pandas, which is a really cool library for manipulating with the data and converting it from one place to another. It is also used for reading our data from CSV file. I used Seaborn and PyPlot for plotting the graphs. You will see them in a little bit. And also I use this missing no module, which is for detecting missing data in our data set. So the first step, I mentioned several steps during the data analysis. This is a feature analysis notebook, Jupyter notebook. So the first thing that we are going to do is actually analyze our data. So the first thing that I've done here is actually I use this pandas function read CSV file to read dataset file, which is called our CSV, and use this head method to display the data. And here you can see that we are having pretty much the same thing that I displayed on the slide. So here are the values of each column, actually of the first 5 instances of my dataset. And then I printed out each type of this dataset. That is because I want to see what do we have in our dataset and how it relates to the real status of it. So actually, I printed out the data types, and I can see that they are all either integers or they are floats, so meaning we are having numerical values. And that is not something that I want. Basically, from the first glance of it, I already know that season is some kind of enumeration, and actually in machine learning we usually call those variables categorical variables because they are, representing some kind of category. So I can say that for several columns here already. For example, I can say that for the month or for the weekday or this weather, how it looked like that day. So in the next step, what I've actually done is I handled those categorical variables. So I defined some kind of map which defines my enumeration. And I've done that for the season and the weather. And I also done some manipulations with the data. Yeah, I'm going to share this code, so you will have it to see in more details. So what I've actually done is I created the list, categorical variable list, for which I said hour, weekday, month, season, weather, and holiday and working day are actually my categorical variables, and I used pandas to switch it to category. And then when I take a look again at my data types, I can see that I've replaced some of the numerical variables with this type category. This will later on, I will do this when I'm building my machine learning model, and this will help my machine learning classes to do the proper thing and to understand what is happening. And now when I take a look, I again use this head method to print out the 5 columns, 5 samples from my data set, and I actually see that for the weekday, for example, now I'm having Saturday, and for the season I'm having like string, which is spring, and for the weather I also have some kind of conditions which are actually describing how that looks like. And now I'm trying to detect the missing data. So for that, again, I can use pandas, which is really important tool that we can have for our data analysis. And I'm actually just printing out. You can see that I printed out if there are any missing data in each of these columns that I have. And I'm having 0 values for them, which is a good thing. It's usually in the real world data, we will rarely have this kind of situation where we don't have a missing data. Usually we are having some kind of readings, but for some sensors, and we are missing readings from another sensors or something like that. So this is like a unique situation. I also can use this missing node that is a module that I mentioned during the importing, and it gives you a nice like diagram which says, okay, if we were having some missing data, we would have like horizontal lines here, and we don't have them because we don't have a missing data here. If we were having a missing data, there are 2 or 3 possible ways that we could handle it. The most common one is to calculate the mean value of that feature and actually use that value whenever we are missing data. So that's what usually we have, what usually we do. And then I'm doing the outliers analysis. That is a part when I'm trying to detect values which are vastly different from my distribution of data in general. So the first thing that I'm doing is I am actually printing out the count distribution. This is done by the library Seaborn. And I can see here in this part, basically it represented like this, and this is represented the majority of values for my count or my output value. But also I'm having these are all separate dots, so these are like the outliers that are out of my biggest part of the data. So but I can see that I'm having a lot of them. So that means that I probably should not remove them from my data set. Sometimes you might want to choose to remove these values which are vastly different from the other ones because they are messing with your model. But also sometimes you want to keep them because machine learning models have this tendency to learn by heart or to overlearn on the, for example, test data, and not to be, they overlearn on test data, and then when you put real data, they give like really bad results because they didn't really understood what is happening in the real data. And what I've also done is I printed count by season distribution, where I can see also that I'm having a lot of outliers, which I cannot remove because there is a lot of them, and they're apparently playing a big role in my general count. But also what I can see from here is that spring is not so popular in Washington for bike rentals. I don't know why, but it is having a lot of less rentals than the other seasons. And then I printed out the count hour distribution, which is really important for me because from this I can realize that it is actually playing a big role. The hour in which we are having this feature is having a really big impact on how many bike rentals were there. So you can see we are having this peak of data around 8 or around 5, which is probably when people are going to and back from work. So I can see that is going to play one big role in my final predictions. And then I'm also plotting out the count per working day distribution, which doesn't tell me much except that on the working day I'm having much more outliers than on holiday. And finally, I'm doing correlation analysis, which is really important step and really cool one, because using this we can actually remove some of those columns and say, okay, if I remove these columns, my machine learning model is still going to do, to have the same predictions or maybe even better ones. So correlation analysis is actually, I can use pandas again and this CORR function, and it will return like how each feature is corresponding to other feature. And I'm using Seaborn and heat map to print out that result of that function. And correlation can go from -1 to 1. And we're actually neither of those values is good, because if we are having -1, that means that those two features don't have nothing in common. So we might want to reconsider what we are having in our data. And if they're having a value 1, that means that they are pretty much the same thing. So in here I can see the temperature, and the temperature is having a value 1, which is expected because temperature is the same thing, right? But also I can see that self-feel temperature and temperature are also having a big correlation, which is 0.99, and this means that I can remove this feature, and which I will later do from building my machine learning model. The other thing that I can notice here is that my count, which is my final outcome, is having too big of a correlation with registered and casual, which is also expected because the count is actually the sum of these two values. So this also means that I can remove these two features from my data set and push it into a machine learning model and have pretty much the same result. And now I will switch to another Jupyter notebook. This one is actually the one in which I will build my machine learning model based on the knowledge that I had from my data analysis. So what I've learned is basically I will not remove outliers. I don't have missing data, which is good. I'm having some categorical, I'm having some numerical values. I need to, modify some data to be categorical, and I can, remove some of the columns from my data set. So here I'm doing the same thing as before. I'm importing some modules which you can recognize from the previous notebook, but also I'm importing Sci-Kit Learn classes. And in Sci-Kit Learn, from Sci-Kit Learn, I'm importing several of the stuff. I'm importing, for example, this train test split method, and that is specific for supervised learning, in which I'm separating my data set, my huge data set that I have, into two big parts. The first one is for testing, and the other one is for evaluation. So what you will usually have in some real world scenario is like client coming to you and giving you just a big chunk of data, and you want to use some of that for learning your machine learning model, and some part of that for evaluating how that machine learning model performs. So this method will actually help us in that, and then separate our data set into two different parts. And then I will import some of the models that I've mentioned, some of the algorithms that I will use, and that is logistic regression, decision tree regression, and random forest regressor. And also I will use this function for metrics and this standard scalar. That is because from the data, I will switch back again, just real quickly. I forgot to say that. So from my data, what I can realize here at the first glance of it is that actually my count is like 16 in this example, and my temperature is 0.24, whatever that is. So it means that they are out of scale. This is probably going some floating value, and I'm having some integer value here. So what I want to do is put them in the same scale. And that is exactly why I will use this standard scalar from sklearn to basically put my data into the same scale. Okay, so load and prepare data. You already saw this. So I'm actually using this read CSV file to import the data, and saying which are categorical ones and use them here. But also I'm defining this array as well, in which I'm defining all the things that I will drop or remove from my data set. That is a date time, which turned out not to be too useful for me. As I mentioned, casual and registered ones. I will remove count, which is my output actually, because I will put it in a separate variables, as you will see later. And I'm removing this self-fill temperature. And also I'm removing this instant, which is just ID of my sample. It is not really useful in this case. And finally, I'm creating output data, which is my count final feature. And my input data I will just remove these things from my data set, as I mentioned previously. So I'm using this drop function. And then I'm using train test split method to actually split my input data and my output data into the input train and input train and output train data, and in input test and output test data. And as I mentioned, I'm using the standard scalar to put it into the same scale. And then we are finally coming to the creation of the machine learning model, for which I'm using predefined classes from the sklearn. And I'm actually creating model, push some data into it using this fit method. And then I get the predictions on the test data using this predict method. So you can see I'm getting some values here. And then I'm calculating that root mean square logarithmic error to get some values. And actually I'm getting the value 1.74. Actually, the closer this value is to 0, the better my machine learning model is performing. So this one is actually performing really poorly on this data set. And then I use the other one, which is called decision tree. Use the same principle, created a class, push train input data and train output data into it, and use this predict method to get predictions on a test, on the test data. And here there are. And then I, I compare that predictions with the real ones from the test data using that root mean square logarithmic error. And I got 0.45, which is much better than the previous one. And finally, I used the random forest. Random forest is one interesting algorithm, which is actually, is assemble of these decision trees. There is like a lot of those algorithms in one. And I can see when I do the same process here, I'm getting 0.35, which is the best value that I got on this data set. Now, this doesn't mean that I'm having too many good hits. It just means that I can have the best predictions using this random forest algorithm. And finally, what I can do is actually I can use improvement analysis. So it is a final step in which I use this feature importances field from the model, from the class of regression tree regressor, which returns to me how much influence each feature had in those predictions. And from this, I can see that hour is having like the biggest impact, and humidity not so much, or for example, holiday is not having any impact on my predictions. So where I can go from here is actually maybe try to remove these features and see if my model performs better, or use some other classes and try to get better results. So I think that would be all. So thank you. So if you have any questions, I'm here now. Or I hope I didn't overwhelm you. What the point was is actually to show you the process, how it goes. And I tried not to get too technical, but I probably did. So sorry about it. Yeah.
Can we get a synopsis of the conclusion? So I guess the hours had the most impact. Sorry.
Yeah.
So can we get a synopsis of the conclusion?
Yeah.
So, go ahead.
Yeah. So the hour had like the most impact in my predictions, which means that this feature I cannot remove. If I want to, get better predictions with this, I would probably go from removing some of these or analyze how these features are affecting the data set. Because if I can get this value with these features, maybe I can even get better, because I will like reduce dimensionality for my model, and that it will perform better.
But if you removed hours, then maybe you'd get better effectiveness of the other.
Yeah. Maybe hour is kind of killing my predictions as well, which is what we saw for the register then and stuff like that.
Thank you.
Yeah.
Okay. I wanted to ask, how do you choose the training data input?
Well, I'm not choosing Git because I'm using this train test split. So in reality, I would get like big amount of data from the client, and I will just take. In this particular case, I use this test size to say that my test size is actually just 30% of the data. So I'm using this method to just create 2 chunks of data. It's nothing smart, just taking 70% of data and say, okay, this is my train data, and 30% of data, and say this is my actually something on which I will evaluate my models.
So it's a random sample, right?
Yeah.
Okay.
So this RMGLE number, is there a direct correlation to to confidence of the prediction?
Yes. In this particular case, it is saying how well my prediction is in regards to the actual values. And in particular case, I'm using this algorithm. I can use different metrics to calculate that. But in this particular case, it is better for me to have overestimates, meaning that the number is bigger, because it's better to predict I have more bike rentals than less and not be prepared for that. So in this case, if I underestimate, it will sort of penalize that value, and the other ones won't get so like won't get looked at it as a bad data, as a bad prediction if it's overestimate. So.
And what would be the process to get something like a percentage confidence of the prediction based on this number?
Like a percentage, you mean from 0 to?
I mean, if you want to say that your prediction model is, I don't know, 85%, can predict a number with the number of rentals with 85% confidence,
okay. So
how do you get to that number?
Yeah, for this one, I would, for example, say that about 70% is my confidence, and that is actually where I actually want to be with my machine learning model, because if I get 100%, that means that my machine learning actually overlearned on the test data, and that is not good. So it's still not that exact. We still don't have that like exact moment in this area because it is still young in a sense of that. So.
Thanks.
Do you think that machine learning is starting to get overused these days? And do you think that it leads to overcomplication to some maybe simpler solutions?
Yes, for sure. For sure. I mean, we are putting things, where we shouldn't put them. For example, I could put the blockchain like Dusan did yesterday in my slide just for the heck of it. Yeah, actually, I think a lot of people are saying that they are using machine learning, for example, and they are just using an if statement. So that's that's not it. But yeah, it has their appliances. But it's not. Of course, it's not a silver bullet. It's up to us as an engineers to see, like, to balance with like with everything we have in the industry at the moment. So.
Thank you.
Just to add on the previous question, so about the 30% of the test data, is that a standard practice or does it depend on the data itself?
It is depending on the data. You basically experiment because you don't know what you have. Sometimes you have just, in this case we have like value, like a label for each feature, but sometimes we just got like, we have to make sense of it, So. What I would say the standard approach is actually taking a little bit less, maybe 80 to 20. That would be like a standard, somewhere where you should start from.
Right. And the other one I wanted to ask is, so in this example, I guess the CSV file wasn't that big. Yeah. But how problematic is it when you have like 50 gigabytes of data that you're supposed to?
To be honest, I never had like 50 gigabytes, so I cannot answer that. But I would probably have to separate it again and do some even preparation that is not maybe programmatic. So I would maybe separate it into separate files and then figure it out how I can glue it together. But Python is really good at that. Actually, he can handle like remember the data behind. So.
Okay, thank you.
Hello. So I wanted to ask a question. So we saw a couple of algorithms that are basically pre-made. Yes, and so I'm wondering, are the algorithms themselves improving now in the past few years, or is it just more like people figuring out which data to take in, and if that makes sense?
Well, in this example, I used predefined. I use this Sci-Kit Learn library. I can also be using TensorFlow, which is Google's library for computing the matrices and stuff like that. And it is used to actually create, let's say, custom machine learning models. But I'm sure that guys from whoever built Sci-Kit Learn is doing some kind of improvements in the background. But the ones that we used are like, how to define, like pretty standard ones, somewhere from point from which you can start, and then you know, go in that process and see if you can use different algorithm or something like that. Also, you can, you know, use neural networks which are achieving the same stuff, but for example, machine learning models in this case are creating those functions mathematically for you know, they take the data and calculate stuff and then create the function, while neural networks are, you know, working on a different principle, and they're probably giving you more like freedom in that sense, that you don't have to think about which algorithm are you using, but you're taking care of different stuff. So.
All right, thank you.
Thanks. Okay, if that's all.
Questions?
I'll be around, so if you had anything else, you can ask me.
Thank you.
Thank you.